In this video, I'm going to go through a quick example showing you how to develop symbolic expression for projectile motion problems, specifically when something's launched at an angle. In a previous video, I've already talked about conceptually how we think about projectile motion when something is launched upwards at an angle or down at an angle. That video is linked in the video description below if you want to go back and review that. We also talked about how to solve a quantitative problem when something's launched up at an angle or launched down at an angle. We thought through quantitatively how to think about the x part of the motion, the y part of the motion, so we can solve for things like how much time will this projectile spend in the air and how far will they travel horizontally while spending that time in the air. Well, in this video, I'm going to look at this exact same problem, something launched downwards at an angle, except we're going to solve it all symbolically. So instead of being given the actual initial velocity, we're just going to call it v sub 0. And the actual starting height, we're going to call it h. And we're going to find an expression for the time that the mountain biker spends in the air coming off of this downwardly angled ramp, and an expression for the horizontal displacement. And we're only going to use the symbols which stand for the initial velocity, the height, and g, which stands for the size or magnitude of the acceleration caused by gravity near the Earth's surface. So let's get started. The first thing we need to remember is that the initial velocity that's given, v sub 0, is not all in the x or y direction. There's a component in the x direction and a component in the y direction. So let's first find a symbolic expression for the x component of the initial velocity and the y component of the initial velocity. If the angle that's given is theta right here, the x component is adjacent to the actual velocity, so we'd use the cosine equation. And setting up a right triangle and solving for vx0, the size of it, is basically just going to be the initial velocity times the cosine of theta, because that's the adjacent side of our right triangle. Well, the initial velocity in the y direction, the size of it, we're going to have to use the sine equation because it's the opposite side of our right triangle. There's theta. It's the initial velocity, the hypotenuse, times the sine of theta. But we have to keep in mind the signs. The way that the problem is set up, the initial velocity in the x direction is negative. So we have to have a negative sign right there. And the initial velocity in the y direction, because it's launched downwards at an angle, is a negative y component. So these are the sizes of the components of the initial velocity, but we need to add the signs. So in the x direction initially, the initial x velocity is negative v sub 0 cosine theta. And we know that in the x direction, there's no acceleration because there's no significant forces in the x direction to speed something up or slow something down. So the final velocity in the x direction will also be negative v sub 0 cosine theta. The initial velocity in the y direction is negative v0 sine theta, like we talked about over here. We don't know what the final velocity in the y direction is. It is speeding up because in the y direction it has an acceleration. The acceleration in the y direction, the size of it is equal to g, which is 10 meters per second squared or 9.8 meters per second squared, but we need to include the sign because g stands for a positive value, and we know in the y direction, the acceleration is negative. It's speeding up in the negative direction. So symbolically, the acceleration in the y direction is negative g. For the change in y position or vertical displacement, it's negative. You're starting at a high y position, going to a lower y position. So it's changing by h, but it's got to be negative h. So let's go through the same process that we walked through in the last video, solving all this stuff quantitatively to solve for the time in the air and then the horizontal displacement. So we have to use the vertical direction to find the time in the air. But when we have a projectile launched at an angle, it's not a one-step problem to solve for time unless you want to use a quadratic formula. We talked about just using a two-step method where you first find the final velocity in the y direction and then use that to solve for the time it takes to travel vertically, some known vertical displacement, or in this case, negative h. So let's use our third kinematics equation and plug in our givens and find an expression for the final velocity in the y direction. So it's the final velocity in the y direction squared is equal to the initial velocity in the y direction squared, which we plug in negative v sub 0 sine theta. That's the y component of the initial velocity. We have to square that. Plus 2 times the acceleration in the y direction, negative g, times the change in y position or vertical displacement, that's negative h. And so if we want to find an expression for the final velocity in the y direction, which will ultimately give us time, we have to square root both sides. And so the left side is just final velocity in the y direction, and the right side is the square root of all of this stuff. But technically it's positive or negative the square root, and we have to decide what the sign is. Well, vertically, it's going to be moving in the negative y direction when it hits the ground, or right before it hits the ground. So we put a negative sign in front of the square root sign. So now we can use this expression for the final velocity in the y direction to solve for time. Let's use our first kinematic equation for the vertical or y direction. The final velocity is equal to the initial velocity plus acceleration times time, all in the y direction. So we now have an expression for the final velocity in the y direction. We just put that in place of the final velocity. The initial velocity in the y direction is in our givens. It's negative v sub 0 sine theta plus our acceleration, which is negative g, all multiplied by time. And so we just need to do a little bit of algebra. We're going to add this to both sides to get rid of it, and then we're going to divide by negative g so we can solve for t. So after a few algebraic steps, we now have an expression which represents the time the mountain biker spends in the air from the moment of launch to right before impact. It's equal to the square root of negative v0 sine theta, all of that squared, plus 2 times g times h, and that's minus v sub 0 times the sine of theta, all over g. Well, now that we have an expression for time, we can now find an expression for the horizontal displacement. So we're looking at the horizontal part of the motion. So here's our second kinematic equation that will allow us to solve for displacement. Displacement is equal to the initial velocity in the x direction multiplied by time plus 1/2 times the acceleration in the x direction multiplied by time squared. Well, remember, in the x direction there is no acceleration, so this whole term goes to 0. So we just get initial velocity in the x multiplied by time. And the initial velocity in the x direction is negative v sub 0 cosine theta, and that's just multiplied by the amount of time it spends in the air moving horizontally. Well, remember, these two times are always the same. The time something spends traveling horizontally is the same time it spends traveling vertically. So all we need to do is take the expression we found for time and substitute it in here. So we basically get this times negative v0 cosine theta. This is what it looks like in the end. One little note of correction. In the problem statement, I didn't include theta as a symbol that we could use, but in this case, we'd have to use theta. And so the problem statement should have said, find an expression for the horizontal displacement and the time using v sub 0, theta, g, and h.